It's Jana Vejpravova from Charles University. We'll talk about the topographic state of graphene, chemistry meets physics. So Jana, the floor is yours.
Good afternoon. I hope you can hear me. Yeah, sounds great. Fine, so thank you very much for inviting me. Actually, I have to say that I'm really feeling like a stranger because I saw like very nice talks dealing with something completely else I'm going to share with you today. However, I hope you will still find it at least a bit useful. Maybe I will start a bit with introduction what we are essentially doing. So I'm both chemist and physicist by education, and in our lab we are mostly dealing with various optical spectroscopies, including Raman and PL, down to extreme temperatures and high magnetic fields. So most of the results I will show you here will be also results from the Raman scattering on graphene. And maybe at this point, I would like to have a general question for a coffee break. What the hell? All the nice systems I have so far seen here have not been addressed by the optical probes. So I hope that somebody will give me answer to that, because I'd be really, really happy and thrilled to look to those systems with our machines. Nevertheless, today I would like to talk about something else. So we have already seen that if we twist two layers of graphene, we can get very fascinating physics. Nevertheless, it has been demonstrated many times before that we can do some similar tricks also if we vary the topography of graphene. So I will summarize some strategies, how we can control the topography, how we can even observe it. In particular, I will talk about how we can disentangle some specific topographic features by the Raman microscopy. And then, of course, there are some other important phenomena connected with that. And this is again something which I already remember from my PhD time when I work in the field of heavy fermions. And there are two important terms, which was the coexistence and of course disorder. So we have already seen today that we also have some new types of disorder emerging in connection with the 2D materials. So I would like to show you that we can even have some kind of mesoscopic disorders if we tune the topography of graphene properly. So you can have coexistence of specific band structure features within one sample. And in relation to that, because my talk promises to get some kind of link between the chemistry and the physics, I will show you how we can use the chemistry and profit from the topographic corrugations of graphene, again, by introducing some functional groups on the surface, or vice versa, how the topographically modulated graphene can influence other species in several processes, like could be melting and freezing, etc. So let me start. I will start from very, very simple thing, and this is the general concept which essentially enables us to predict how the graphene layer, or in general any layer, will look like if we place it on a substrate. And just depending on the elastic properties and the adhesion between the layer and the substrate, we can tune the state, the final Ruga state, by many means. So here you see some examples. I would like to emphasize that this is a kind of general concept. So of course it works for graphene, but it can also work for much larger objects, as it is shown here. And how we can really do it in practice? Of course, quite simple way how to do it, and which is in fact a really elegant way, as I have to say, is to introduce some defects. So if we are able to introduce periodically ordered defects in graphene lattice, of course, as a consequence of having the defects in the lattice, we end up finally with periodically corrugated graphene. And it has been already demonstrated many times before. So I have picked up here the nice work of Professor Guinea, published 10 years back. So if you have such kind of topographic corrugations, what you observe in the band structure of the system is that you will see pseudo-Landau levels. So that's really something which we are used to observe in magnetic field, or in these some very exotic states, which can be in fact maintained when you twist the two graphene layers, for example, as we have seen today. However, you can really create similar features simply not by just putting the graphene proper angle with another layer, but just by deliberating the graphene from the flatness and making some engineering of the corrugations of the surface. So let me proceed further, and I would like to show you some experimental strategies people are using. And the first one is essentially very simple, and it's something which has been introduced in 80s, 90s, when people were trying to shape different thin films of anything. And the trick is that you place the layer, in our case, it is a graphene, on flexible substrate, and the substrate is pre-strained. So if you look here to this kind of general VUCA diagram, so now we are like working in this area. So if we just maintain all the conditions or the parameters properly, which means the ratio between the modulus of the film and the substrate, the mismatch strain, of course, some normalized adhesion energy, we can end up with a system which looks like that. So simply you let the substrate relax and you create some hierarchy of wrinkles, these topographic states. This works nice, but it's not really very efficient for most of the experiments. So we have to do it slightly different way. And if we'd like to transfer this nice topographic landscape on a substrate, which is useful for various treatments or experiments later. So the trick is that you profit from having just creating these kind of wrinkles with the help of a polymer, but as a next step, we place it on a substrate. So we can create such quite complex structures. The disadvantage is that we will always end up with the graphene, which is really strongly corrugated, and we cannot really have some areas which are completely adhered to the substrate, which sometimes is beneficial, especially when we want to treat the graphene later by some chemical means. So there is another possibility how to do it, and this is quite simple and straightforward. Instead of using the polymers and just tuning the mismatch strains of the substrate and the graphene, we can just simply use a decorated substrate. So you use a substrate, you deposit your sources of corrugation, which could be particles, could be fluorines, just can be anything you can imagine. And on top of the decorated substrate, we transfer the graphene, and as a result, we can control the amount of the corrugations on the surface. So this is something which is quite powerful, and it has been demonstrated that for the graphene monolayers, it works quite nicely. Nevertheless, I have seen that the graphene bilayers nowadays kind of highlight. So I would like to show you that in fact it's in principle possible to apply the similar approach also for the bilayer graphene. So instead of placing the sources of corrugation on a substrate, we can first put a graphene layer, then just introduce again either fullerenes or particles on the bottom layer, and then on top we add another one. So in fact, you can imagine that we have a structure when there are areas where the two graphene layers are stick together, so they are really in direct contact. However, there are some areas when the graphene layers are separated by either particle or the pivot or whatever you can just place in between the two layers. And now the question is how to look inside, how to really investigate what happens inside. And this could be a kind of problem, because I have mentioned that just beside the transport measurements I'm not going to discuss today, we are mostly using Raman spectroscopy. And for the Raman spectroscopy, if you imagine that you shine the laser on such a system, such a structure, you will definitely hit both layers because they are atomically thin. And of course, even with the best confocal microscopes we are using, we will always hit both layers. So there is a kind of trick how we can do that. And because we are mostly looking to phonons, we can simply color one of these two layers. So we can engineer the lattice the way that we replace the atoms by atoms of a different mass. As a consequence, the phonon frequencies will change, and then we can very conveniently address those two layers within our experiments. So instead of using two carbon-12 layers, we are using carbon-13 and carbon-12, and we can then nicely detect those two layers separately in the Raman spectra, as it is shown here. So they are the representative spectra in the area of the G and 2D modes. I'm not going to talk about in detail where they are coming from, because I believe this is something very well known. But it's important to mention that we can nicely trace the top and the bottom layer separately with our approach. So why this is useful? So now let's have a look to what happens if we try to map the sample. So we scan over the sample, which is composed of the two graphene layers, isotopically labeled, and they are locally glued by the particles, for example. And if you look to the map of the Raman intensities in the position of the top layer and the bottom layer, so this is corresponding to the carbon-13 and this is the carbon-12, we can find some areas where we see strong enhancement of Raman signal. And also the shape of the peaks here is different comparing to some standard Raman signal from the samples of a monolayer, for example. And those features here comes from the fact that we have a convenient twist angle between the bottom and top layer. In other words, when I just switch here to the slide where I just try to represent what's happening, In our case, we are simply matching the laser wavelength with the energy separation of the Van Hove singularities, which creates simply because of the specific twist angle within the two graphene layers. So just by tuning the laser energy, we can select on the samples the domains with different twist angles, and vice versa. If we know for which laser we have resonance, we can determine what is the twist angle in these areas. Nevertheless, I forgot to mention the other contribution or the other feature which we have in this sample, and those are these corrugated areas. Of course, we cannot really easily see them on these, let's say, dominant G-mode maps. Nevertheless, if we inspect more in detail the fine structure of the Raman mode, we can easily recognize some kind of extra band which appears here. And this is the band which is typically corresponding to those corrugated features, because if we apply some advanced analysis, just the convoluted strain of doping, we can really clearly say that the band coming here comes only from the graphene, which is accommodated in the rugas, in the corrugates on the surface. So this is also very nice that we can separately look to the bottom and top layer, and we can also disentangle contributions from the flat areas and the corrugated areas in the sample. So then I will just skip to another example. So I'm not going to discuss in detail what happens if we just place graphene on such pillars. Essentially, it works in the same way, just by changing the parameters of the substrate. So it means the pillars, dimensions, and also their distribution on the substrate. We can create many different states. But when we looked more into the detail in some of the samples, we observed that there are some quite unusual features. So I will just directly skip to the slide here, but I would like to show you what happens. So sometimes if we create wrinkles, what can happen is that it can make some kind of collapsed state. And the collapsed state is stable as far as the height of the wrinkle is about 8 nanometers. If it exceeds that height, it just makes this a kind of wall. Nevertheless, if we look from side to that wrinkle, we can say, well, so it's simply the same like we would have a bilayer, twisted bilayer. And if we inspected these samples more in detail with our probes, so I'm not going to just describe here the AFM imaging, I will go directly to the Raman. So here is a scan along such kind of collapsed wrinkle, as we can call it. And then there are areas where we see, first, extreme enhancement. So this always suggests that there should be some kind of resonance with the laser, which will tell us roughly what will be the mutual orientation of the layers. And second, we observe here some extra bands. And all these extra bands coming from the processes outside the Brillouin zone are always a signature of a specific twist angle in the graphene bilayer. So by scanning along the wrinkle, we can just go point by point. We can identify in every region what will be the twist, just depending on the excitation energy of the laser use, and also depending on the position of these extra bands, because their position is also driven by the twist angle of the graphene bilayers. So I will just skip probably this slide here, and I will stay with the rugas. So I will stay with the corrugation. And in the beginning, I have mentioned that probably it can be useful to show that all these games are not bringing only kind of interesting physics, but they can be also very useful if you would like to modify the properties of graphene by introducing some functional groups. So this is well known that if we are introducing fluorine, for example, we change to insulating state. If we introduce hydrogen, we could have even magnetic states, etc. Nevertheless, it can be also interesting to see if we can do it selectively. So if we can do it with a kind of resolution. So for that purpose, we made the first study on the samples of graphene, which were transferred on a substrate decorated with the objects of different size and different distance. So here is some example. And we applied both the hydrogenation and the fluorination procedure. And it can be very nicely traced that with increasing the amount of the corrugations, which is something we can also identify from Raman spectroscopy. So if somebody is interested, I can come to it into discussion. But nevertheless, with increasing amount of corrugation, we also observe that we can introduce more hydrogen and fluorine on the sample. In other words, it's in fact something which we would expect. Like if you have more corrugated state, so it means that you have more graphene which is bent. So the p orbitals are labilized. It means they will be much more prone to undergo the chemical reactions, so uncover the chemical species on the wrinkle. So this was really a nice confirmation that if we just enhance, or if we just enhance the reactivity locally by local bending of the graphene, we can much more easily introduce the chemical functional groups only at the position where the graphene is strained. So this is a kind of like general picture, and the last slide I would like to share with you. So I will just jump to some kind of conclusions. So today it was really a hard task for me because I saw that I should probably choose completely different topics for discussion here. Nevertheless, I hope I have shown you that in principle, if we are just trying to topographically make some kind of topographic control over the graphene, we can reach some spatial modulation of the doping and the strain. And of course, it has many consequences. Regarding the band structure, this is quite clear. We can reach some Van Hove singularities, or we can even reach the Landau levels with our ferromagnetic field for some specific shapes of the rugas. Nevertheless, it has also other impact. For example, we can influence chemical reactivity locally. So we can switch the system from like the standard state, having insulator or even a magnet. And finally, there are some other important points. This everything like which is here is of course ringed together, and there are some other features which I would like to emphasize, and this is specifically at the point of corrugation. So if we are using some objects for the corrugation, there could be some local extra interaction. So if we are using, for example, fullerenes, there is nothing that special, just there will be some kind of like charge transfer effects. Nevertheless, if we are using magnetic objects, there are sources of local time-dependent magnetic fields. So that's something which we can also introduce in the system. And on the second hand, I had no time to discuss today, but also the topographic features, if they are able to somehow imprison some other species like molecules, they can also strongly influence their behavior, their thermodynamics. So this can be even used to really change the thermodynamic properties of matter. So I believe that I just tried to convince you that also the topographic modulation of graphene is still something useful. I would like to thank my collaborators, mainly from the Hayrovsky Institute of Physical Chemistry, Martin Galbach and Otta Frank, expert on this kind of strain effects in graphene. We also had collaborations with Leibniz Institute in the nanopolar synthesis. And of course, some of the work was done quite a long time ago on MIT in collaboration with the group of Drezelhaus and Jin Kong. I would like to thank, of course, our funding and to you for your kind attention, and happy to answer your questions if there are any. Thank you.
Thank you very much for a great presentation. So the session is now open for questions. Any questions? Maybe. Okay, I'll start with a quick one. So you're putting these objects under the graphene to induce corrugation. So, but you also see. So you might have mentioned that, but like, what is also the influence of, like, there's also some chemical influence of it. How do you distinguish the corrugation from the presence of the other material? Do you distinguish, or?
Well, so I mean that if you just have the substrate and deposit the particles or fullerenes or whatever in clean room, and then you place the other layer on top of that, there is really not reason to have there some extra chemistry. So if you are like, it's like if you transfer normal graphene, instead of having a flex substrate, you just transfer it on the particles. Of course, there are some post-treatment procedures, like some annealing, etc., which just when we are able to get rid of some like extra hydrocarbons, for example. But that's really something. If you always transfer graphene substrate, it's something which is always there. So this is something you do not detect really, because the traces or the amount of this like extra chemical species, as you call them, is there. Other point is that, of course, if you measure on the air, I think much more influences the doping from the air and from the substrate than from some extra tiny amount of some remnants of the transfer if they are in it. So then this is really not important. If you start to introduce the functional groups, there are like fingerprints in the spectra, for example, so you can look what happens with your demo. This is indirect evidence that you are encoding some species, but there's nothing else that you are locally printing a defect. So this is not that nice confirmation. So then the standard way how to do it is to investigate the XPS. So from the XPS spectra, you can quite nicely determine the amount of fluorine, of course not the hydrogen, but with the fluorine, it's something quite standard that we can do. So that's it. So I think it's nothing special like.
All right.
Standard.
I have a question, Madam Andrea Perali. Yeah.
Please. You have a so I have a question here on the chat from Milovan.
Okay, I wanted to give the word to Andrea, but I will shoot a quick question to Jana. Jana, thanks very much for a very nice talk, and I think your talk is important to this community much more than you realize. You will see already in the next talk the relation immediately. But just a quick question about those nice ridges that you showed, a couple of nanometers tall and a couple of nanometers broad. How long can those be in your experiments? I mean, what you have seen so far.
I don't want to say infinite, but for me, like when I consider my resolution of the experiment, could be 10 to 100 micrometers. If
okay, that's like exactly what I was looking for. Okay, thanks very much.
It just depends what you need. We can retune many different means. I had no time to introduce really the details, but essentially you can really cook the system on purpose if you are looking for. Even for a specific angle nowadays, we are able to do that. So the samples I have shown were just some like random transfer of CVD graphene. So just by chance, in some domains, we got some twist which we could see by the resonance with lasers. But nowadays we have the dry transfer, and we can even have much better control over the twist angle. So then it is even possible to like do the systems more sophisticated than it was like 2-3 years back.
Sure, thank you.
All right. Andrea, maybe a quick question.
Yeah, I'm Andrea Perali from University of Camerino. Really, congratulations for this talk. So to understand better, so are we in the position to experimentally control and tune the curvature of a single bubble of graphene on top of a substrate with nanoparticles, fuller ends, or others? Is it possible to tune in a controlled and continuous way?
Yes, indeed. When I will speak like in some kind of average numbers. So if we like control the concentration and position of the objects and size of the objects on the substrate, we can really tune it. Of course, there is some limit. So if I will say, okay, we start in, if you have standard CVD graphene, there are still about 2 to 3% of corrugations. This is which we know from AFM. We have some experiment where we determined it directly from Raman spectra. I had no time to show, but we can discuss later. So it's quite simple way how to derive it. And if you start to put the objects of your, let's say, desire and put the graphene up to 60% of corrugations, there is perfect control. So it works. If there are more objects, more particles, then you have some extra phases, I mean, the topographic phases, because then the graphene is not in perfect contact in the areas. So the graphene is already delaminated completely if you have too many objects. And of course, it relaxes and it just creates some secondary or even higher hierarchies of the corrugations. So the states are much more complex. This is something what I have shown for these pillars. They are already high, so if you put the graphene there, so it just hangs, and then there are all these like first, second order, whatever hierarchies creating. But if you keep some reasonable size of the object and reasonable concentration, up to 50% of corrugation, we are fine. So we can create it. It's not a problem.
Okay, thank you very much.
All right.